plans? Well, they would, in helping you to design it, they would go back and consult the soil survey and use all that same information. So that's where we start, and that's the purpose of that information. That's the purpose of these activities. They're not just kind of random things to keep you busy. And the other thing is we go back, and I've tried again to connect all of those things back to the performance objectives, which I've given you for the class. And so if you can connect what we're doing and look back and say, oh yes, I see how that connects to one of those performance objectives. Why those performance objectives? Those are the things that consulting agronomists have agreed are the things that somebody who wants to become an agronomist should have as a background of information and knowledge. Well, with that, let me talk about drainable porosity a little bit. And in starting, let's go on. So, you know, I've gotten questions about it. It's difficult to find a table on it now that tells you what's there. So again, I'm going to present some information about how I did it. And then I'll also post a little bit later today some general estimates on drainable porosity based on soil texture classes. Those are generalizations because it's going to depend on a lot of things other than just soil texture, but that's a good starting point. Why is it important? Again, if you're designing a drainage system from scratch, you need to know how much water will flow out of that soil when you put a tile down there. And so that's why it's going to be important to us. So if we start, let's review a little bit what we did in the very first part of the semester when we were reviewing things and talking about soil properties. So if we go back and we think about that cube, we look at that and we know that there are 3 phases, but let's just start with the first phase, that solid phase. Well, the difference in what's in that solid phase and the total volume, well, that's the volume of the pores. So let me try to make this a little, see what we can show up here. Yeah. So in trying to convert my office into a lab, I went out, I'll show it from the top to the bottom. This is just a fluorescent tube container cut off, and then I bought some sand, and this is a fairly coarse sand, and I filled this tube with that sand. This tube is about 50 centimeters long. That's about 20 inches, and it's filled with sand. So I've got the total volume. That was fun. How did that happen? I have no idea how they did that. Interesting. But I've got a total volume, and that's just the volume of the tube from where this sand starts down to the bottom. So that's the total volume. That volume is occupied by, particularly here at the top, because it's dried by evaporation, it's occupied by solids and spaces between the solids, voids, those pores. And the pores are relatively large because this is a coarse sand. And we've talked about difference between sizes of particles and sizes of pores. So these are relatively large pores. Now, if I want to know the porosity of the soil, that's the volume of the pores in this soil relative to the total volume occupied that soil is in. So that includes both air and water. In order to find that, we have our definition that we used. That is the volume of the pores divided by the total volume. So the spaces between the particles and all the particles. So this height and then the spaces between them, that's our porosity. And we had a calculation that we used to estimate that porosity. Now, then another concept that we talked about is a saturation percentage. And in that case, what we're asking about is how many of the pores in that soil are actually filled with water. And again, we had a way to estimate that, to calculate that. That's my definition. And then in order to calculate it, we used a different formula. But that tells me of all the pores in this soil, how many of them or what percentage of them are filled with water. So with those two concepts, that gets us started on how to think about drainable porosity. Now, what happened the other day is I filled, after I made those, get this sort of organized again. After I constructed those, that was on Saturday afternoon, I believe, maybe Sunday evening. After I constructed them, I filled them with water. They were already wet. Two of them particularly were already wet when I put them in because they were bags of stuff that had been outside in the yard at Lowe's, and so they weren't dry when we started. Ultimately, I'll get them dried, but we started with those, filled them up, got them saturated, and then I collected the water that flowed out of them. So let's kind of work through that process. Pardon me just a minute. And all that I did, somehow that ended up out of sequence. Let's move it to here. All right, sorry about that. So we start with something, let's start with an oven-dried soil. Now our definition of a dry soil is that it's oven-dried, that it has no water in it. So you've just got solids and spaces between the solids. And so the total volume is just the volume of the solids plus the volume of those pores, and the volume of pores are all filled with air. Now, when we move from that to an air-dried soil, and depending on the texture of that soil, the air-dried soil and the relative humidity, the air-dried soil will have different amounts of water in it. So if we look here, now we've added a little bit of water, and the total volume, the volume of the pores are now filled with air and water. And then the total volume of the soil is the volume of the solids, plus the volume of the water, plus the volume of the air. Now let's add some more water to that soil. And let's move up to wilting point. There's more water in the soil at wilting point than at air dry. If you dry a soil to one point and then you allow the environment to keep drying that soil through evaporation, you go from, that's the difference between wilting point and air-dried soil. So air-dried soil has a little bit of water in it. And then wilting point is the place where plants cannot extract water anymore. It's too dry to get water out of it for a plant. But the air can evaporate more water, so it can take more water out of the soil. And we still have the same thing though. The total volume of that is now composed of solids, liquids or water, and air. Now let's continue here. Now let's move up to field capacity. We're adding more water at each stage. Field capacity is what, and the difference between field capacity and wilting point, that's what defines for us the plant available water. Now what's field capacity? Well, field capacity then is the difference between the water left in the soil after the gravitational water is drained. So the gravitational water drains out. And once we reach that point, so we had gravitational water here. You can't see it when I'm pointing at it. You have gravitational water there. And then the difference between that gravitational water, it's going to flow out of those larger pores under the influence of gravity. And when that happens, you're at fuel capacity. And the difference between fuel capacity and wilting point is the amount of water that the plants can use. Now, I'm showing this to represent saturation. Notice that the soil is not completely saturated. Now, I've taken some pictures of this. I haven't been able to convert those pictures yet from a picture in my camera, my phone, to picture added to the diagram. But to give you the idea, and the one that shows up best in is the one I did with the gravel. Now, all the water that will flow out of this gravel has flowed out of the gravel. But when I first saturated it this morning, put the water in it all the way up to the top. Again, this is about 50 centimeters or 20 inches. Filled the water all the way up to the top. And then I open it up and I let it drain, and I've caught the water that drained out of it. The water is draining under the influence of gravity. So this gravel does not have an ability to hold much water. We have to go back and think about capillaries. Those smaller pores are the ones that hold water. Larger pores are the ones that allow water to flow out. Drainable porosity is going to be related to the amount of water that will flow out of that soil under the influence of gravity. When gravity no longer has enough energy to pull the water out, then that's as much as water as you can actually drain from the soil. So now, let's see if you can see here on this one. If not, again, I've got pictures that will allow us to see it. You can see a line right about here. Like the others, I filled this tube up to the top. So I mostly saturated the soil. It's not completely saturated because it did not have, there was air that would be trapped in those pores. And I've allowed it to drain. And you can see kind of a couple of marks in here, one of them relatively up about here, and the other one right here. So what does this represent? The water that would drain out of this soil by gravity is the water that drained from here to here. That's all the water that would drain out of this soil under the influence of gravity. So if my tile line is represented by the bottom of this, the soil is not, at that tile line, is not going to be completely dry. It's not even necessarily going to completely reach the fuel capacity. It'll be wetter than that. When I've lifted this up out of the water, my hand is getting water in it. And again, that's the soil below a tile line would be saturated. And so that water will be pulled up above that water table, even at the bottom of the tile line. So when you put in a tile line, you are not drying the soil to the depth of that tile line. You're not even introducing much oxygen to the depth of that tile line. Because if there's any saturated soil, the soil will pull the water up. Again, we're going back to thinking about capillarity. It pulls water up above the level of the water table. Now, let's go back here. And so the gravitational water represents that drainable porosity. So the drainable porosity is the amount of that water held in the soil that will drain out of the soil profile when we put in a drainage tile. So again, thinking about that, We started up here at 0, and we're going down, and those marks are every 10 centimeters. So we get down to the bottom there, and I've got about 20 inches that I'm working with. And so if I started up here at 0, and I've allowed the water to drain out, this is going down to about, it's going down to about 46 centimeters. That's going to be about 18 inches. And so when I put in a tile line, that's what this space at the bottom will represent, I was able to lower my water table in this coarse sand by about 18 inches, 46 centimeters. So again, that's going to represent my drainable porosity. How much of the water can I move out of the soil? When we look at this other one, I was only able to move the water out down to about, I've got two things in there. It's still really wet, below about 36, and you can see another line in there at about 26. And so putting in a tile line in this fine sand, putting in a tile line at 18 inches or 20 inches, it only lowered the water table about 14 inches, 36 centimeters. And this soil is still really wet, probably a little bit above field capacity, all the way up to about 26. So what's the amount of drainable porosity? Well, and if I look at I calculated the volume of those cylinders, and then I measured how much water came out of those as they drained, and an equivalent amount when I converted the milliliters of water to centimeters. In that coarse sand, what I got out was about 15, equivalent to 15 centimeters of water. That's the water. But but the water table dropped for me about 45 centimeters. So I may see a 45 centimeter drop in the water table. And again, that's going to be in the vicinity of 18 inches. So I can drop the water table by 18 inches, but I only got out this much water. Actually, this much water. And getting out this much water, the water table dropped. Again, drainable porosity. In that finer textured sand, I only got out this much water. But in getting out this much water, I lowered the water table this much. So the idea of considering the drainable porosity is trying to understand how much water do you need to get out? How much water can you get out of that soil? And using these, I know that if I need to lower that water table 2 feet, if my water table needs to be at least down to here, well, in one of those soils, I can get away with having my tile just a little bit below that. In another one of those soils, see, I said we had one down to, what was it, 26? Yeah. If I put the tile line at 50 centimeters, I've only effectively lowered the water table about half that, maybe slightly more. So that's why I'm doing this stuff, trying to understand soil properties, looking at those, trying to figure out what is the drainable porosity, how much, how deep do I have to have that to get the water table to be as deep as I want it, to allow that plant to have enough oxygen in the root zone for that not to be the limiting factor for growth. Now, so if we go back, think back again, stuff that we were talking about in the first unit. And also we've talked about that in assignment 3, where you had to find field capacity and wilting point. And if they were given in percent or inches per inch, you had to then figure out how many inches or centimeters of water, available water, you had. Doing the same kind of thing that I'm talking about here. How many inches of water does that represent in a soil profile? Now, so we started with an oven-dried soil. This also goes back, this just takes out the cube and all the other stuff. We start with an oven-dried soil that has no water in it. Depending on the soil texture, we go from oven-dried soil to wilting point. Now, at the wilting point, and this again goes back to that first unit thinking about it, wilting point is controlled by, hang on just a moment. All right, this is controlled by soil texture. And particularly the clay content, because the clays are the smallest particles. The clays bind the water most tightly, and the clays release the water most with the greatest amount of difficulty, takes the most energy to take the water away from the clay particles. So wilting point is determined by soil texture. Then a soil that has more clay has a higher wilting point. So soil texture, particularly clay, and soils with more clay hold on to more water at wilting point. Then we go up to field capacity, and field capacity is controlled more by soil structure. Because field capacity is going to be related to the pores and the water that will stay in the pores, the size of the pores, and because bigger pores will allow water to flow out under the influence of gravity, smaller pores will hold on to the water by capillarity. Water will be trapped within aggregates. And then depending on the size of the pores between the aggregates, water can be held in those, or water can flow through. So we're talking about structure. Oh, that was fun. Hang on, let me figure out how to get this to come back so I can work on it. There we go. And in structure, we're talking about aggregates. Somehow or another, I lost my pen. There we go. So in structure, we're talking about the aggregates, the size of those aggregates, and that's what determines the size of the pores. And so the difference between field capacity and saturation, that's going to be related to our pore size. Large pores. Because, so if you're taking notes on this, you've got this diagram roughly put in. I'm going to erase these words so that now then you can see the next part where I've put some things in on my slide to demonstrate what happens next. So I'm going to erase these things. Now, what happens next? Those large pores allow water to flow out under the influence of gravity. that water that flows out under the influence of gravity is what we're measuring and talking about when we think about drainable porosity. Then the water that's held in the soil between fuel capacity and wilting point, that's my plant available water. Wilting point is controlled by soil texture. Fuel capacity is controlled primarily by soil structure. The amount of water that drains out of the soil is affected by soil structure, large pores. And so again, if we think about a soil, we think about big pores and small pores. The big pores are the ones that allow water to flow through most freely. And so a very simplistic diagram, they're not showing many real difference in the sizes of the sand and silt clays at all, or silt particles at all. But bigger pores, more water flows out. Macropores flows out under the influence of gravity. Intermediate sized pores, less water flows out under the influence of gravity, or a mixture of pores, bigger pores and smaller pores. The water flows out of the smaller pores. Try again. Water flows out of the bigger pores and is retained in the smaller pores. And then with a clay, if you have poor soil structure, not many big pores, the water is going to stay in that for a while. And if you have a shrink swell clay soil, when those clay particles swell, they close up any pores that might have been in the aggregates, and now water just sits there. It just ponds there and can pond there for a long time. At this point, let me open it up and ask for see if you've got any questions. You can feel free to open your mic and talk to me, or you can open up and send me a text or a chat. Let's see then something else that might be here. I'm organizing some stuff here in Excel so that I can, I can see what I'm doing and show you some, how I got to some information on an estimate of drainable porosity. So if you'll bear with me a minute, let me get my Excel sheet set up. How can we tell which soils benefit from drainage and the types of drainage? Okay. Not sure what you meant with the part of types of drainage, so give me a little more information on that. Which soils will benefit from drainage? Great question. Let me get through some other stuff here. Let's go back and talk about the drainage, the drainable porosity again for a moment. Come on. All right, I need to share. All right, this is taking information from my assignment 3 that I gave to you as an example. And if we'll look through this. Just going to take these first few columns of information. I think we'll stop here. And you've got, as you were working through your assignment 3, gathering data, you collected this depth to a restrictive layer. Why is that important? You can't put a tile line below a restrictive layer. It won't do any good. And if you've got a shallow restrictive layer, it's going to be difficult to tile that soil effectively. You have to lay the tile on top of that restrictive layer. because water is only going to go down as far as that restrictive layer, and then it's either going to pond and come back up, or it's going to move laterally if there's any kind of a slope to it. So if you do have a restrictive layer, you lay the tile on top of the restrictive layer. And in some of these, if we look through here, on these particular soils, my restrictive layers, there we go. On these soils, then the shallowest restrictive layers I have are here and there, 127, and those are in centimeters. So that's going to be about 4 feet-ish. 100 centimeters is about 40 inches, and 27 centimeters is about 10 inches. So 50 inches. So again, a little bit more than 4 feet, or about 4 feet. And so if your restrictive layer is that deep, that's not a problem in putting in a tile system. But if you've got a restrictive layer at 24 inches, that's going to be a problem for your tile system. You'll probably have to put the tiles closer together, because there's not a lot of space for the water to drain downward under the influence of gravity. And you need to introduce some oxygen. Then there was the question related to, the types of the drainage classes or types that we had there. So which of these soils on my site that I collected, and this is out by Lexington or Livingston County. I think that's on the other side of the county. Then my soils here, I have only 1 or 2 moderately well-drained soils. I don't show the acreage and extent of these, I see. So if my Varna was occupied a large amount of the area, I probably would opt to leave that one out. But it may be that the slopes are so complex, I can't leave that one out. Notice also that it's one that has a higher slope on it, 4 to 6%. The other moderately well-drained one that I have is a silt loam that has a 2 to 5% slope. And then I go to those 2 that are the somewhat poorly drained soils. Note all of those are silty clay loams. And then I've got 1 poorly drained soil that's a silty clay loam. So I can see that my soil texture is making a big deal. My soils that have more clay content have, actually one of those is very poor with a silty clay loam. It's probably got some other stuff, probably has a silty clay in the subsurface. But the finer, finer textured soils have poorer drainage than those that are coarser, and a silt loam isn't much coarser than a silty clay loam. But if you think of your texture triangle, as you move upward in the triangle, you're increasing the clay content. And so the difference between a silt loam and a silty clay loam is at least 10% clay content. So as you increase the clay content, the drainage gets poorer. The landscape position also has some factors that'll affect that. Now, then we've got this next component that says the K-side of the limiting layer. Okay, I know my limiting layers now are at these depths, some of them greater than 200 centimeters is on the order of about 76 or so inches. On the order of 80 inches. And so those are really deep, not a big deal. And actually the limiting layers have a relatively high, in this one, has a high hydraulic conductivity. And these 3 their hydraulic conductivity is much lower, much slower. And so those restrictive layers are going to be a little more limiting to water movement. So if this one weren't on a slope, if this Varna weren't on a slope, it would have a major drainage issue because it's got a low hydraulic conductivity in the limiting layer. The limiting layer is within 40 inches of the surface. And so it would have some challenges. But its other issue, the water table is fairly deep for it. So all of these three things are coming together to affect the drainage class. The depth to the water table, the one that we don't have on there is how long that water table hangs out at those depths. And then how fast the water will flow through that soil, like KSAT, of the limiting layer particularly. And then the soil that's affected by soil texture. And then the slope, because if I've got a slope, my external surface drainage is pretty good because the water is going to move away from the soil surface. Now, okay, where are we next? Does that mean a restrictive layer can act similar to tile drainage systems if they are positioned right? The only way a restrictive layer can help you is if it is on a downward slope, because then the water will hit the layer and then flow downhill under the influence of gravity, even within the soil profile. But no, a restrictive layer, if it's anywhere close to the surface, actually enhances the need or increases the need to put in a drainage system. Now, all right, let's move over. I didn't have you let's kind of make these a little bigger maybe. All right, so I did not have you go in and I didn't have you pull out the bulk density from your in web soil survey. So I did this as an example, and then I used that bulk density to estimate or calculate the porosity. Now these bulk densities are relatively high, but they're going to look probably represent a soil profile. And even though they're relatively high compared to what you would find in the surface, they're not uncommon for what you would find at, say, 50 centimeters and below, or 18, 20 inches and deeper. The bulk densities are typically higher. Now, so I started with bulk density, and you remember in that presentation I did, we started with talking about porosity and how you would calculate porosity. That's what I did here. And were I to, pull up the formula there, you would see that what I did is I said 100 times, and then I took 1 minus, and here's the bulk density, 1.46, and then I divided by 2.65. So I used that to calculate the porosity. Those are, again, that's the best way that we have to estimate porosity. It's not an absolute number, but it's the best we can get. And then, if I take care of my misspelling there, all right. So then I got my porosity. well, I go from the porosity, and now I've got field capacity here. So again, the field capacity is the amount of water left in the soil after the gravitational water has gone out, which is going to represent my drainable porosity. So of those pores, on this soil, I'm ranging from about 9 to 15% or so of the pores will be drained under the influence of gravity. Now, what that's going to amount to, and knowing the percentage is not that helpful to me, but what that amounts to is, if I take my soil profile and I'm going to put my, for ease of what I'm thinking about right now, if I've got my soil profile and I put in my tile system at 100 centimeters, I'm going to use that just because it's easy math. That's about 40 inches. And I can drain 10% of the pores under the influence of gravity. That means I'm going to take out 10 inches of water, 10 centimeters of water, or about 4 inches. So the drainable porosity is what determines how much water will move out of that soil. And we saw earlier that if I can take out on the examples that what I showed you is if I took out 6 centimeters of water in that sand, I lowered my water table by about 26 or so, 30 centimeters. And in the really coarse one, if I took out, what was the number? And in the really coarse one, if I took out 15 centimeters of water, I lowered the water table by 45 centimeters. Well, those have a much higher drainable porosity than these soils. So, and what's affecting that? Our soil texture, any kind of other things that will make those layers more difficult for water to move. Let's see if there was so that's an estimate. And again, trying to explain to you what drainable porosity is. And if you're ballparking a number for drainable porosity because you don't have one, well, here you can see that it's probably going to range from about 9 to 15% on the upper end. I have another table that I'll pull up for you, but again, those are without doing a lab study and analysis, you're not going to have an exact number that you can find. Then we did field capacity, we did wilting point. We use that. You can calculate the percent available water is the difference between field capacity and wilting point. And then if you have a rooting depth, let's see, what did I do here? I put a rooting depth in. No, so this was something else that you could get. If you know a rooting depth, you can estimate then the amount of available water in centimeters. That goes back to another one of those calculations that we made in thinking about soil water in that first unit in soils review, because you look at the profile depth and then the volumetric water content. So again, let me use some easy numbers. If I had a 100 centimeter soil profile and I got 9% of that is available water, 100 times 9 is 9 centimeters. So this one is looking at something probably on the order of about, actually that's a really deep profile, 2-point-something meters. But that's how you can get from one to the other. So that's how I used my assignment 3 data. I went back to Web Soil Survey and got one more piece, but to get an estimate then on what my drainable porosity would be. And that's assuming, when I'm making my estimates there, my assumption is that the porosity that when I started at saturation, that all of those pores are filled with water. That's not going to be the case. Some of the soil will never be completely saturated. It'll always have maybe 3 to 8% water, air in it, even when it's essentially saturated, because you've got small pores that are filled with air, and the water kind of occludes them and keeps them from getting connected